All right, class, ready to get started? All right, good to see everyone again. Few announcements.
How was it?
Which is good. Yeah. It was good time. What's that?
It doesn't say anything.
Yeah. You know, there's some good talks, so students from my lab.
We invite all and
What's that? I mean, what's that? Yeah, it's a good call. What I said. All right, few announcements so to get started. Homework 9 is out. Homework 9 will be due on Wednesday. I know, it's on Wednesday at midnight. I know many of us are going to be gone by Wednesday at midnight, but you have everything you need to do homework 9 now. So you can get started on homework 9 today if you want. Homework 9 is an individual assignment, right? So last week we had the CFD part 1. This is back to the individual assignment. And just as a heads up, the last problem involved aspect of revisiting the homework, the problem from the exam. But for parts C and D of this problem, I'm asking to solve it in ASCII instead of solving it by head. Okay. So you'll go back through A and B, which give you the numbers that you need to plug into C and D, and then I want to set that up and solve it in ASCII. Just like Professor we discussed on Monday. Any questions on this? Okay. CFD project part 2. This will be a group assignment. Project assignments are coming soon. I think I mentioned last time they've changed a little bit. I have to finish going through all the revised web resources that will be part of your assignment for CFD project part 2. Midterm 2 grade have also been posted. Mean this time 76, standard deviation 15. So if you're more than 1 standard deviation below the mean, we should talk. Again, just like midterm 1, and I'll be reaching out to these students, but you know my email's coming, just get in touch with me, please. Finally, this just came out, but there's actually breaking news on the equations that we developed in this class. A reminder, the Navier-Stokes equations are nearly 200 years old. And the Euler equations, what this is about, are actually even older than that. And so the news about the equations that we studied in this class really does not happen often. So this is kind of related to the Millennium Prize we discussed, where there are some key questions about the existence of solutions to these equations. And a team of mathematicians have shown that the Euler equations, the Navier-Stokes equations without the viscous term, do actually blow up under certain conditions. There are certain initial conditions under which the Euler equations do not give a viscous term. This is still in the process of being verified by other mathematicians. The proof was so complicated they had to use a computer to basically do a lot of the calculations for them. But it does appear to hold. Basically, they set up a flow where they had 2 spirals of fluid initially moving in different directions on the top and bottom half of like a cylindrical container. And then they let this evolve over time, and in the absence of friction, so there's some secondary flows that are created. But that's generally true. This would be true inside of a coffee or tea cup as well, hot chocolate cup. You get these secondary flows, but in the absence of viscosity with the Euler equations, they've shown that you end up with vorticity within the system growing and growing and growing without bounds, going to infinity, and that's impossible. It's physically impossible. Therefore, it's a major result. Anyway, just there's more information here if you're interested. Sort of a popular science article about it. Yeah.
Question about the CFD project.
Yep.
For the tutorial, it took a whole bunch of people like dozens of hours to do the iterations on the group pool, but we were able to download like a student version that took 5 minutes to do all the iterations. Are we allowed to use that, or does the functionality?
You are. So the major limitation of the student version is the number of nodes in the final solution. You're only allowed to have up to 512,000 nodes in a solution. In a problem set up on the student version. I've asked the TA to go back and look at their problems from last time to see if they exceeded that number. And I'm still waiting, that's one reason why I haven't signed projects yet. So I have no problem with using the student version as long as it lets you get to the answer.
Okay.
Other questions? Yeah.
Could you post solutions for the second midterm? It's hard to tell what we miss points on grade scope when we only get positive for stuff.
Sorry, when you only get what?
When you get positive points for stuff we did do and not like sections that we missed. It's hard to tell which of like the categories we missed each problem.
If you didn't get points for it, then you missed it.
Because you only add points for
Yeah, but can you see, are you able to see the whole rubric on Gradescope? Like, are you able to see the points that you missed as well?
you can see the points that weren't assigned to you, but there's also like partial. Like it adds up to greater than the sum of the points.
It's like there's no specification on what you needed actually to.
Okay, yeah, I'll post this. I have to put them in a meter form and then I'll post. You're right.
Can we expect to have a group assignment for Thanksgiving? If we want to work on it over the week.
Yeah, definitely. You will definitely have this for us here. Yeah. Other questions? Okay. All right, so today, we're going to just go over a very brief introduction to computational fluid dynamics. Just to follow up on what you've done, what you've learned from going through the tutorial, and also just integrate this with the lecture on Aspen last week and kind of place all of these things in context. Your textbook discusses CFD chapter 8.9 just a little bit, just the basics. And we're really not going to go beyond the very basic concepts in CFD today. All right, so and just to take a step back and where we're going. So we've covered now through chapter 7, right, which is external flows. This is really the only topic we're covering from chapter 8, and then we're moving on to chapter 9, starting on Monday. So we'll start talking about compressible flows. The goal of this class is to build your background, basic introduction to fluid mechanics. Right, so we've been going through derivations, so you know where the equations of fluid mechanics come from. Remember, the main thing that I'm concerned with is that you know what expression to start with, like how to start problems, how to set up problems in fluid mechanics. And the derivations, my intention is that with those derivations, you see when those different equations are applicable or not. And then we do problem sets using those kinds of things to practice the concepts that we talked about in class, right? That's the general principle. But in sort of the real world nowadays, computational tools are very widely in order to solve problems, and there's that's no exception in fluid mechanics either. So we've kind of very briefly introduced 2 tools here in this class just within the past week. The first was Professor Whitty discussing Aspen, which is a tool that uses essentially a control volume type approach, like our chapter 3 type approach, in order to solve some problems. And you've done a tutorial now in ANSYS Fluent, which uses a differential approach, right? So essentially it's based on the equation that we learned in chapter 4 in order to solve problems. So to get back to what we're doing in this class, basically try to make sure you have a solid grounding in the fundamentals that underlie these things, so that you can understand and interpret the outputs of these kinds of computations. Because one of the things we're going to talk about today is like, how do you know that the solution that you get from, let's say, fluids is not wrong? And there are some things that you can do to kind of check that. But another thing that's you need to know what all the inputs and what all the options are before you can use these kinds of tools responsibly. And so even though we don't really go in detail into computational tools in this class, the basics, the fundamentals that you learn here are setting you up for being able to use something like this in the future. And this field of CFD, computational fluid dynamics, which is really what's covered in ANSYS, or what's being performed in ANSYS Fluent, is really a topic, an entire topic unto itself that builds on what you would learn here. So you can take entire classes on these topics. But let's go back to Aspen. So in Aspen, we can model pipe flow, right, which is primarily the object or objective in chapter 6. So we can do modeling of relatively simple pipe systems in Aspen Plus, which is a tool that Professor Whitty introduced on Monday. So for example, this will let you solve a type 1 problem where we're solving for pressure or head. I can tell you now that on the midterm, problem 3, both parts C and D were type 1 problems, so you'll be able to solve them in Aspen Plus. Right, so the types of problems where you don't need iteration, we can directly solve in Aspen Plus. But there are tools available for more complex problems. In particular, Aspen HiSys is an add-on package to Aspen that Professor Whitty documented to, which will let you solve those more complex problems that require iteration. So, including pipe sizing and iterative solutions to flow rate type 2 type problems. But just a word of disambiguation. So Aspen is a computational tool, right, that allows you to solve pipe flow problems as part of more complex like system design, right? So when you have a pipe linking different elements in a chemical plant or something that you're designing, Aspen can help handle what are the pressure drops, what are across all of those, right? How much energy are you using due to pressure drops across those pipes? And so Aspen solves the balance equations, just the same ones that we've developed in class, and the same ones that you can use by hand, the same ones that you use on the midterm 2, problem 3. And then we'll do all the work of looking up the friction factor for you. It also has built-in loss coefficients. Some manufacturer data is built in. You must input your own if it's not available there. And additionally, it's capable of both component and compressible flows, something which we're not covering in this class, and something which we're going to cover in chapter 9. Can also be handled by Aspen. So it's a very useful computational tool. Chromax, right? It's another option instead of Aspen. But Aspen and Chromax are not computational fluid dynamics. Okay. So they are computational tools, but they're not what we would call CFD. So in CFD, we're going to be solving the differential equations of fluid motion. Okay, and that's what you were doing in the tutorial. So for example, we can solve for an arbitrary geometry, like the intersection of some pipes, right? Like you did in the tutorial. We can solve for the flow, velocity, and pressure profiles within arbitrary geometry using computational fluid dynamics. So as an example, let's consider a diffuser. So a diffuser, we have low speed flow, incompressible flow, or just flow with Mach number less than 1. Then diffuser is what we would use to reduce velocity and increase pressure. So we have flow here from left to right. That's initially, so by mass conservation, we know that the flow leaving this diffuser section must be at a lower velocity than the flow through the initial lower area region. And for a second here, ignoring the impact of friction, one major effect of this would be to increase the pressure, right? Speed goes down, pressure goes up. So this is what, so that's what we're looking for ideally. Within the diffuser, this is more realistic, where there may be some separation that occurs at the walls, leading to some pressure, some friction, which would reduce the pressure recovery of our diffuser. You know, and that's generally what's going on with it. So if we know, so if you're trying to design a system using a diffuser, right? We have a pipe network, there's a diffuser somewhere within that system. And if you know the performance, right, if you're using a standard design, then you can use Aspen or Promax or another solver, right? Take an approach like an energy balance type approach to incorporate that element into your system. You know, look up the data on the table or use pre-programmed data lookup tables in order to simulate the performance of the diffuser and use that kind of solve. Right. Use a an energy balance or a balance equation type solver. But if you're trying to design a diffuser that has some unknown design, right? Like instead of trying to, if this is for a straight diffuser of standard, standardized shape and size. But let's say you need to design a diffuser that turns some bend and has this kind of like weird square duct shape because that's what fits into your system. And you don't know how this is going to perform, right? You don't have good data on how this is going to perform. Then that's when you might want to use CFD, right? Or an experiment, but CFD is often a lot cheaper to get started. For example, ANSYS fluids, right, which you've been working with, which is a finite volume method solver. But basically, it means that this is a way of solving the Navier-Stokes equations, right, with the equations of fluid motion within this arbitrary geometry. And one thing that we can do with this kind of solution is then figure out what is the actual pressure difference across the diffuser. What is the actual performance of the diffuser? And then plug it back into some kind of a solver like this. Yeah.
I just want to make sure, so when you say performance, do you mean knowing like the inlet and outlet pressure and velocity?
Yeah.
Okay.
Yeah, that's what I mean. Right. So the point of a diffuser is to increase the pressure, right? By doing a mass balance across the inlet and outlet and using Bernoulli, you can estimate what the sort of ideal pressure increase would be. It's never going to be exactly that because there's always going to be some frictional loss. And so the performance of the diffuser in this context is like, what is the actual pressure? So if we have some unknown shape, we want to know the performance of this unknown shape so we can put it into our system calculation. Then we can solve for the performance of that unknown shape using something like a CFD method. Yeah.
Sorry, again, to clarify, is the performance just the actual increase or comparing the actual increase to the ideal?
It could be either. I mean, depending how you define it. But just in general, trying to set up the idea that of the relationship you might have between these two types of complications. Because it would probably be pretty cost prohibitive, be very expensive in terms of time, calculation time and setup time to simulate your entire chemical plant using CFD. Right. So we probably want to simulate the entire chemical plant using the balanced approach of Aspen or Promax. But if we have individual components where we need to know what's going on within those individual components, we need, where we have unknown performance, we're trying to optimize performance somehow, then that's where we use CFD. So in CFD or computational fluid dynamics, generally, we mentioned this when we were in chapter 4, generally we know the equations. Equations for an incompressible Newtonian fluid, for example, is just the Navier-Stokes equation we derived in chapter 4. So it's not like you're trying to find the right equation to use. We know the right equation to know them from there. So yeah, it's Newtonian and incompressible, we're going to use Navier-Stokes. So that means that in setting up CFD, it's really all about the boundary conditions and the grid that we're going to use, the grid over which we're going to do our computations. So these are really the main things that you'd be changing from problem to problem. this is really setting up CFD. You don't actually spend that much time worrying about the equations that you use. Really spend most of your time working on setting up the right boundary conditions. And especially building your geometry and your mesh.
For the grid, what exactly does element size affect?
We're gonna talk about element size quite a bit more because, so now, we've discussed boundary conditions, when we were in chapter 4, after we introduced the Navier-Stokes equations, we talked about boundary conditions. The same type of boundary conditions that we use, like no slip condition, inlet or outlets, flows, or, the condition at a free surface, those same types of boundary conditions that we use to solve problems by pen and paper are the same, are what we would use in a CFD solve. So we have discussed boundary conditions, but grid is something that we haven't gone over and something that you need to understand. But so these two things are the main things that are actually changing from problem to problem, right? The equations stay the same, but the boundary conditions in the grid determine what you want to see. And this grid, or you'll hear me call it a mesh, or you'll hear it called mesh as well, is basically how the solver, or how the tool ANSYS Fluent or other CFD solver is going from the partial differential equations, Navier-Stokes equations, to ultimately a set of linear equations that it's solving at each individual grid element, or set of simplified equations solving each individual grid element. And then it's solving those, a set of equations at each little grid element, essentially doing a balance, taking what we've learned basically from chapter 3 and doing like a little balance of mass, momentum, and energy if you need it, across each individual grid element within your problem, based on the Navier-Stokes equation. So these two things are going to be really where you spend most of your time, and really the grid and geometry is going to be the main thing you spend time on in setting up CFD. So so again, we've discussed boundary conditions, right? And the same general principles about boundary conditions that we learned for pen and paper solutions apply for CFD. But for meshing, there are a number of things that you need to keep in mind. So you'll often see an option about resolution. Like you might have some kind of a resolution option when you're meshing things. Like is it fine or coarse? And that has to do with the size of the grid element. So if the grid element is larger, we call that coarser. If the grid element is smaller, we call that finer. Question is like, how fine is fine enough? That's something we're going to discuss on the next couple of slides. So that's really a key question here. You'll also, another thing that you'll be able to set typically if you're setting up your mesh is the rate of change of mesh element size as you transition from a fine element grid to a coarse element grid. So this comes from your tutorial. And you can see that we have, for example, a fine grid, a fine mesh inside of the small inlet tube, transitioning to a coarser mesh in the larger tube. So one of the things you can control is actually the rate at which the elements change size. You can also typically choose the shape of your grid elements from rectangles or prisms, right? So rectangles in 2D or prisms, rectangular prisms in 3 dimensions, or triangles and tetrahedrals are the other option. So as a rule of thumb, rectangles or rectangular prisms are better. They're better behaved computationally than triangles and tetrahedrals. But triangles and tetrahedrals are easier to set up. So oftentimes if you're doing some automatic meshing, then it will automatically mesh your geometry using triangles or tetrahedrals. But this can lead to numerical errors and inefficient calculations. So whenever possible, you want to use rectangles or rectangular prisms. Yeah,
So what do you mean by near walls?
so, so you want to be using this kind of shape whenever possible. But especially near walls, so if you have, so that means like when we're close to the boundary, so,
Flat walls is the two?
in this case, we're using actually rectangular shapes.
Okay.
Everywhere in the walls. And that has to do with the fact that we typically have a boundary layer near, a wall. Remember, in a boundary layer, the rate of change as we move, or in general, when we have a solid surface, the rate of change of our solution as we move away from the wall is much higher than the rate of change as we move along the flow. So typically then we'll have elements that are stretched out along the flow, which you can actually see. So very typical of CFD type mesh. And so I take advantage of what we know about boundary, right? What we know about the possible solution, and using rectangular elements, which tend to be better behaved numerically. So one reason why they're better behaved numerically, without going into all the details of what exactly is going on within your solver, is that this issue of skewness. So skewness is something that you'll see as in your if you're looking at your grid quality, you'll see that it will report the skewness of your grid. This is a major factor in mesh quality. It's basically like how stretched out, how unequal, how sharp the angles of your grid are. If you have really sharp angles like this is a really, really poor mesh element. This has to do with the fact that your solver is trying to balance flows coming in and out of this through all the different faces. And having these faces that are such different sizes and at these kind of extreme angles gives rise to numerical errors. This kind of element here would give rise to many numerical errors. And you're likely to end up with a lot of these if you don't carefully mesh using tiles. This is what a high skew element would look like in quadrilateral or a rectangular mesh. Quadrilateral. So you'll see skewness as an output. I want to give you, so there's, and there are many concepts, right? Just meshing alone is something that we can't cover in a single slide, can't cover in a single lecture. This requires quite a bit more information in order to really be able to do well, but I just want to give you a sense of something to watch out for. Yeah.
So a couple things like with the mesh, so in general, like will ANSYS fluids tell us that there's an issue with skewness?
Sometimes.
Okay.
So solver may tell you that there's an issue with skewness. Most of the time, though, it won't. You'll just see. So one thing that you might see is that you're having a really hard time converting. Okay. Now it seems like on our grad pool, there's what issues with convergence anyway, because the calculation takes a very long time. But if you have a calculation that is just not getting close to convergence, then oftentimes the cause, or one of the things to look at with the skewness of your elements. Yeah.
When it says that after it converged, it wasn't able to reach the specified like.
This could be one of the
Is
reasons.
that one of the?
This is
Okay.
one of the reasons why a solution will not converge.
Okay.
Another reason maybe your elements are not smaller.
Okay.
Confusingly, when you have a time dependent solution, another reason maybe your elements are too small. Again, yeah, we can't cover all of this in one.
And so kind of going off like the air issues with the mesh, would it be, it's like on ANSYS, but there's an option when check the quality, there to improve the quality. So in general, does that work really well, or should we like, is there?
So an option to improve quality will generally work. It may not get you all the way to what you need. So I want to give you, what I want to give you, my main goal here is to give you a more general framework without a complete understanding of CFD. That's impossible within the time we have. But a more general framework for understanding how to use CFD responsibly. Okay, and it starts here. with, and how to interpret. So even if, so and another thing, you may think, oh, I'm never gonna do CFD myself, right? I'm gonna keep that to someone else, I don't like this fluid stuff. But you will, in your career as an engineer, encounter CFD, and you have to ask the right questions about those solutions, right? Let's just take it at face value. So in general, if we're setting up a fluid problem, any problem, pen and paper or CFD or ANSYS or whatever, you're going to make decisions, or the person who's done it and who's presenting the work to you is going to make decisions in setting it up. Okay. Some of these can and should impact the solution. Right. So like physics-based decisions should impact the solution. If we choose to solve for pipe flow and we use water or we use honey, right, we should get different answers. This is the viscosity difference between those two. If we change the geometry, right, we do your mixer example from the tutorial, change the geometry. You should be getting a different solution. If you make different assumptions about the governing equation, you assume it's incompressible, or Newtonian, or non-Newtonian, right? Then that can and should impact your solution. Right? However, there are many decisions that you make in setting up a problem in general, but especially in CFD, that are not related to the approach, that are not related to the physics, and therefore should not impact your solution. And these are the ones you really, really have to watch out for, right? So it's relatively, these can be very hard to, these can be harder to evaluate. But once you agree that you have the physics set up correctly, you still have other decisions to make. It's a list of some, okay? So it includes the origin, the type of coordinate system, right? So are you using Cartesian or cylindrical or spherical, or Eulerian, Lagrangian? You know, what type of coordinate system are you using? Typically, we're doing Eulerian when we're doing CFD, but in setting up problems on pen and paper, sometimes we do things in Lagrangian. The order in which you solve the problem. So oftentimes in a computational solution, you might be trying to solve for multiple physics, or you're doing heat transfer and fluid, and fluid, right? In each order. You can choose the order in which those equations are solved. That shouldn't have an impact on your solution, but it could. It's something you have to check. Discretization, we're going to spend time again talking about grid size. But like that, the size of the elements in your grid should not impact your final solution. But it will impact your calculations, so you do have to pay attention. Another big one is size of domain. Like if you're simulating flow over an airplane, right? It's in this really, really large atmosphere. You can't simulate like the entire atmosphere just to do a calculation around a single airplane, right? That's way too computationally intensive. So you have to have a finite geometry size, finite domain size, in order to run that simulation on a computer, right? And so that's what we call far field boundary. You have to make sure that the size of your domain is not impacting your. Just because you chose to only make your domain 10 meters above and below the airplane, you have to make sure that that's not giving you some weird results. Another issue here is fully developed flow. So one of the boundary conditions you can specify often in computational tools is that the flow profile, you can either specify the flow profile of the inlet or to specify that it's fully developed. You have to make sure that that's not having an impact on it. So yeah, so for example, we have flow around the cylinder, right? Not even air flow, just flow around the cylinder. We have uniform flow coming in, and we're saying this is in some really large domain. How big you actually make it in the tool, in the computational tool, is a decision that you have to make. You have to make sure that that decision doesn't impact the answer for like what drag you predict. So you've seen this before. This is one of the reasons why I have you do over 5 problem 1. This is a pen and paper analog of this, where you had flow in coordinate system 1, right? We were looking at flow between 2 flat plates. I asked you to solve it in coordinate system 1, where y is your variable here, starting from the wall. And I asked you to solve it again where your variable z starts from the center between two plates. You get answers that maybe look different, but I ask you to show that they are actually the same, right? Because this is a decision that does not impact the physics of flow between two flat plates, and so should not impact your final answer. You can show that with pen and paper. So real flow doesn't care, right, where you draw, what you define as z or y equals. So you should get the same answer in either case. Okay. But real flow also doesn't care if your grid is 2 times as small. Like the thing you're trying to simulate is independent of the size of grid that you decide to input into your simulation. So you have to make sure that your solution doesn't depend on the size of the grid, because the real flow doesn't depend on the size. So the general framework here, general thing to keep in mind is that if these approach decisions, these decisions that you make that are arbitrary, not physics based, if these things impact your solution, then that's a potential problem. If you haven't checked that these things, that your solution is independent of these decisions that you've made, then you have a potential problem you just don't realize. So this gets to this idea of how do you know to trust your solution, right? Like it's relatively easy. This may be computationally intensive, and there's a lot of graphics and stuff here, but it's relatively easy to get some, sometimes referred to as total fluid dynamics, simulation or visualization of a flow that looks beautiful, right? In some sense. And your computer will calculate the result, the velocity, the pressure, everything you want to know about this to machine precision, right? To 3264 bits, right? You'll get an answer far beyond 3 sig things, right? But how do you know that it's actually right? So here's someone, arguing vehemently against just accepting this kind of thing. Just because the numbers are presented to somebody that different digits doesn't mean you should just accept the answer. So there are steps that you need to take to responsibly use computational fluid dynamics. And if someone's presenting to you CFD, these are steps you need to check as their manager or as their coworker, in order to understand if this is actually something that's finished. So validity of inputs, right? All the physics-based decisions, check those, make sure those are correct. You have the correct equations, correct boundary conditions, correct fluid properties. It's kind of the easy ones. The mesh quality, we're going to talk a little bit about this. So that would be, making sure you don't have elements that are highly skewed. This is something that, for example, ANSYS can help you with a bit. Convergence analysis. We're going to talk about different types of convergence, okay, and what those can mean. And then finally, comparing to known solutions. Right? So you're going to be doing this in your CFD project. But generally, when we're doing a CFD study, first you simulate something where you know the answer. Right? We don't do CFD for cases where we know the answer. We're designing a diffuser, right? We're not setting up, in the industrial type setting. We're not going to be setting up a diffuser simulation to validate the thing that's in your textbook, right? The table or chart that's in your textbook. Right? You're doing it to design something new. But before you can design something new, you have to show that you can get a result that's known and ideally similar to your solution, and then start making changes to get towards the case that's actually unknown, the case that you actually care about. So this is how we validate CFD setup. Make sure that those decisions that you've made are not impacted. It's one important way to make sure the decisions that you've made are not impacting your simulation. All right. So before I believe this, I want to see a lot of things. One of them would be, okay, well, how well did you do on predicting the drag force on last year's model of car versus what you actually saw? And then you're going to show me this for this year's model of car. Okay, yeah, then you got it right last year. You did basically the same thing this year. That now. So in general, we're doing this when there's no known solution. So you start with a similar known case, and then extend to the unknown desired case. Okay. Incidentally, this means you're probably going to end up spending most of your time with that known case, because that's where you're getting everything working. And then extending to the unknown case, the thing that you actually really care about is going to be smaller times. All right, so one thing that you're going to see and that you saw on this on the tutorial is convergence of your calculations. And so this is a plot of residuals of your calculation versus iteration. This residual is basically just a measure of how much the solution is changing from iteration to iteration. So another decision, right, that you're making in the calculation, or that the computer's really making, is how many iterations. And this is the automated check that your solution is not changing very much as you increase iteration. So that's an arbitrary decision, not based on physics. And this is done more or less automatically by any CFD. Right? It checks that your solution is flattening out. We're typically see this on a log scale. So as we're getting towards these really small numbers on the log scale, even if the slope is still going down, then typically these changes are really, really tiny. And so we would say that the solution is converged when we get to small residuals with iterations. This is somewhat analogous to the convergence of like solutions for friction factor, right, in our calculation of pipe flow. But notice, like, let's see, on exam, I told you I would never ask to be more than one iteration. Just told me you needed more. And in class, we never did more than like 3. But in a CFD solution, you may need many. Right? And this is checking convergence across many of the things we have. Right? So many more calculations. So this kind of convergence is important. Right? This is kind of like the bare minimum convergence for CFD solution. But the other one, another important type of convergence is mesh convergence. This is not automatically done by ANSYS. Not automatically done by your CFD, but it's really important. So, the question here is, how do we know that the mesh size, the grid size, or if we have a dynamic solution, the time step that we chose, you have to set like what is the TT, the delta T that you're going to actually do your calculation. How do you know that number is not affecting you? Or the size of the domain, or whatever it is. How do you know that these things didn't affect your solution? Well, best way to tell is to measure. So, if we look at some output variable, maybe we're looking at flow around a cylinder. Maybe it's the drag force on the cylinder. Okay. We're looking at flow through a diffuser. Maybe it's the pressure drop across the diffuser, or the ratio of pressure drop across the diffuser to the ITO. Take that output number, some number that we can compute, hopefully that we're interested in from the simulation, and plot that as a function of the thing that we know shouldn't affect our solution, but might. Right. So it could be the grid size, it could be the time step, it could be the domain size. And generally, you're going to see this kind of plot where increasing fidelity is going out to the right, so meaning like smaller grid size, smaller time step, larger domain. What you'll see in this kind of a plot is that the thing you care about, force on the cylinder, the pressure drop across the diffuser, will change as you change this protocol. But it should approach some kind of an asymptote. What we would say is that when you get to some point where you're within some tolerance, it stops changing terribly much, then we're going to say that's probably good enough. In this case, like if this was the so we might plot this parameter as 1 over grid size. Right, so this is called the convergence study. So we might have like output flow rate versus 1 over grid size, like 1 over the average size of a grid element, minimum size of a grid element, or something like that. Or this might be output flow rate versus number of grid elements, right? In your or drag out wall versus the size of the domain. Right? And so this would be a convergence study that would tell us that ideally we reach some point where ideally, we're able to reach some point where our solution is independent of that. So one question is, why not just use a crazy small mesh or a huge domain? And the answer is that calculations are not free, right? So this is the plot from a real calculation of, so the peak vertical deflection, this is a solid mechanics simulation, same idea. The peak vertical deflection of some kind of element that's under bending versus the number of elements in the mesh. You can see it's converging. Okay. But in green here is the amount of time it takes for the solution. Right, you can see that flows up as we increase the number of elements. So we're looking for a case where we have a good enough mesh size, domain size, whatever it is, to get an answer that we believe, and then that's probably where we're going to do our calculation. Because generally, if we're doing a CFD, we don't just simulate one thing, right? If we're designing a diffuser, we might test dozens of diffusers. One of the reasons why I use computational tools instead of experiments, right? We test many things. So you want to figure out what is the domain size that's going to give you an answer that's good enough, right? That's independent of your mesh, but it's not going to take crazy long. Is there a question? And I will ask you to do this. This will be an element of your project, right? Part 2. It will be a mesh. So there are many elements, right? Many things you may actually really need to do this for in a real world CFD. I'm just asking you to do a mesh convergence or grid convergence study for that project. Okay? So I'm looking for a plot like this, showing that you have achieved mesh. One thing that we would say is that here, the answer, we don't necessarily know if it's right yet. At least we know that it is mesh independent, meaning that or grid independent, meaning that the solution does not change as we refine our grid. All right. Final note before we break for today, just about turbulence models, because you will encounter this in your CFD as well. There are many different options in ANSYS Fluid. I just want to define those for you. Many of them are range models, right? So like kappa epsilon model is generally a good starting point for a turbulence model. It is a RANS model, or Reynolds average Stokes model. And it's basically using a set of semi-empirical equations to compute these terms here, which are the influence of turbulence on the mean flow of turbulence stresses. So, but all of the different RANS models are different ways of modeling this. They've been developed for different types of flows, or better, different types of flows. Flows around airfoils, or flows or internal flows, or that. You will also see an option for large eddy simulation models. And large eddy simulation models actually simulate not only the mean flow, but also the largest turbulent eddies that we have within the system. And then they model everything, they use the turbulence model for everything below a certain critical size, for all the turbulent eddies below a certain critical size. These can be higher fidelity than the RANS models, because you're actually simulating some of the turbulent flows. But they tend to be much more computationally. So I'm using the model here. So we talked a little bit about direct numerical simulation. That's where we don't model anything about turbulence, where we just directly simulate average Stokes. This is typically the domain of mostly academic research still to this day, but at some point this may be more commercial. So just a word of caution: the choice of turbulence model is another one of these decisions that shouldn't have an impact on the solution. But it does. So this is contours of turbulent kinetic energy. So this is like how much the turbulence, one measure of how much the turbulence impacts the mean flow. But now computed for different types of turbulence models. So these are different types of RANS models. You can see very different profiles, right, depending on which one you're using. So details of how you make this decision are unfortunately beyond the scope of this class. So in the class CFD project, the tutorials will specify what you should be using. Follow that for now, but just know this is another one of those decisions, right? The physics of what's really going on here, right? What really happens in this flow if you run it in a wind tunnel, what this is happening within a piece of equipment that you're trying to design. Those real physics don't care what Rand's model you chose, right? What often you chose. So this should not impact your solution. All right, that was a very brief crash course to see if you had any questions or anything before we break. Okay. All right, thank you all. Have a great weekend.